In this section, we're going to look at the difference of two means. And remember from when we looked at one mean, we would look at the t-distribution. So both the t-interval as well as the t-test. Over here in this study, we're looking at a stroke stent study, and we have two groups. So we have a random assignment to a standard care group, and we have a second group that receives a standard treatment and a stent. They then measured the mean disability score on a scale from 0, which means no disability, to 7, death. And the question is over here, does this new stent treatment lower the mean disability score? So we are looking for a lower score in our treatment group compared to our control group, which was the standard care. So when we look at our results over here, we can see that our stent group has a mean disability score of 2.26 with a standard deviation of 1.78, and there were 98 patients in that group. Our control group has a mean disability score of 3.23 and the same standard deviation of 1.78, and there were 93 patients in the control group. So our sample data looks good. Our stent group seems to have a lower mean disability score. And now the question is, does that mean that this is a superior treatment? This is not just sample fluctuation, but there's really a difference between those two treatments, the standard care and the new stent treatment. So let's fill in some of these parameters. So our mu1 is the population mean for our stent group. Mu2 is the population mean for the control group. Both of those are unknown. Our standard deviation for both groups are also unknown. Our sample size is 93 for the control group and 98 for our treatment group. Our sample mean is 2.26 for our stent group, and it is 3.23 for the control group. Our sample standard deviation is 1.78 for each group. So, could the difference have been by chance alone? Or did the stents actually improve patients' outcome? That's really the question we're looking at when we're looking at a hypothesis test, looking at the difference over here, right? We understand that differences within samples happen, so we have normal sampling variability, but is the difference in our results due to that sampling variability, or is it due to a difference in the population? So let's consider the sampling distribution for a difference between two means. As long as our samples are independent simple random samples, we know that when we take repeated samples from that same population, we subtract the means of our two samples, we know that sampling distribution is going to be centered at the difference of our population means, so at mu x minus mu y. And moreover, we know that when we are putting two data sets together, whether we're adding or subtracting, we always introduce additional variation, which is why when we're looking at the standard deviation of this, we're actually finding the square root of the sum of the variances. So this has to do with the fact that when we're taking the smallest value and we're subtracting the largest value from it, we end up with smaller values than our original data set. And when we take the largest value and subtract the smallest value from it, again, we end up with the widest range of values. So this is the reason why we add those two variances when we're finding that standard deviation of that sampling distribution. So if our sample size is large enough, and we had our rule of thumb of having at least a sample size of size 30, same thing holds here when we have two independent samples. Each needs to be a sample size of at least 30, or both distributions come from a normal distribution. So if that holds, then the sampling distribution of the difference of x1 bar minus x2 bar follows the t distribution with a mean equal to the difference in population mean and the standard deviation equal to the square root of S1 squared over the sample size N1 plus S2 squared over the sample size N2. So again, that comes from the formula up here where we're adding those variances. And remember, when we're looking at samples, then our standard deviation gets divided by the square root of n. So sample 1 is when we take our sample standard deviation S1 and we're dividing it by the square root of our first sample size. When we're squaring that, we end up with S1 squared divided by N1. So this is how we get to our first part underneath the square root, and then we do the same thing with our second population. So let's look at how that affects our hypothesis testing. As before, we set up our null and our alternate, and we start by comparing the two proportions or the two means, and they can either be equal or, mu1 could be greater than, less than, or not equal to mu2, depending on what our claim is. So we look for keywords like greater, less than, or differs within our context of our data. So in our context, we wanted to know if our treatment group, which was mu1, had a lower mean disability score than our control group over here, mu2. So that would be our alternative. Mu1 is less than mu2. Now, if we can prove this, then we would say that yes, our new treatment would be superior to our old treatment. So again, the idea would be to try to hopefully reject the null and have sufficient evidence for our alternative hypothesis. To calculate our test statistic, we take the difference in sample means. We're going to subtract from it the difference in population means. Keep in mind that mu1 is equal to mu2 per our assumption in the null hypothesis. So that means we don't have to subtract anything. And then we're going to divide by that standard error which we looked at above. The calculation for the degrees of freedom gets very complicated. However, technology will give us the degrees of freedom, so we're simply going to skip over that. Some stats textbooks have a simplified version looking at the lower of the two sample sizes and subtracting one from it. Again, that would be, a simplified formula, but technology will give us the correct degrees of freedom. If we have some additional information about the standard deviation and we can assume that the standard deviations are the same for our two populations, then we can use a pooled variance. However, this requires making an additional assumption, so we are not going to use it. Just a quick little side note. So how do we find the p-value? As before, we're going to look at our test statistic t, and we're going to find the tail area. So if we have a right tail test and we have a positive test statistic, we're going to find the area to the right. If we have a left tail test, we're going to find the area to the left. And if it's a two tail test, we're simply going to double that area. On StatCrunch, we can actually go to the t-stats, going to two sample with summary, or if we have our data, we can use our data, and that's going to calculate our test statistic as well as our p-value. Or on the TI-84, we can use the two sample t-test. So let's continue on with our stroke study and calculate the test statistic and calculate the p-value. Let's go over to StatCrunch and plug in our information. Going to Stat, T-Stats, This time we're looking at 2 samples. We have our summary statistics, and our first sample mean for the stent group was 2.26. The sample standard deviation was 1.78. The sample size was 98. Our second group, which is the control group, had a mean score of 3.23, a standard deviation of 1.78, and a sample size of 93. We are doing a hypothesis test to see if the means are the same. So either mu1 is equal to mu2 or mu1 minus mu2 is less than. So again, mu1 being less than mu2 because our first sample mean is lower than the second sample mean, and we want to know, is the population mean for our treatment group lower than for our control group? And when we're subtracting those two, we end up with negative values. So we need to have a less than symbol over here. One of the graphs I always like to look at is the p-value plot over here. So we're going to consider that. And we see that our test statistic over here is negative 3.764. So just looking at that test statistic, usually we have values between -2 and +2 that are considered usual or ordinary values, and anything less than -2, anything greater than +2 is kind of considered unusual. And we understand that those values shift around depending on our significance level. But over here, this is negative 3.764, which is an unusual value. It corresponds to a very low p-value of 0.0001. And if you go over to the right, you can see the p-value plot. Since we had a left tail test, our p-value is just a little tiny area in that left tail. So let's go back and write down our test statistics. Since we're looking at means, we're finding a t-test statistic. It's negative 3.764. Again, that's an unusual value. Unusual values correspond to very low p-value. And over here, 0.0001. So we wanted to know, did this difference just happen by chance? And looking at this p-value, since this p-value is so low, we would conclude, no, it didn't happen by chance. This is less than or equal to our significance level, in which case we're going to reject the null. And when we reject the null, we would say at the 5% significance level. There is sufficient evidence that the mean disability score for the stent group is lower than the mean disability score for the control group, for the old treatment. So that's good news. So definitely this new treatment seems to be superior to the old treatment.